The sun. It's a source of energy for life on Earth and is made from the two simplest atoms, hydrogen and helium. Even so, the sun exhibits complex structure and behavior. Within its core, temperature and pressure are so high that hydrogen nuclei are fused into new helium atoms, generating deadly gamma-ray photons. The photons must then pass through the dense core and a section of the sun called the radiative zone. They are absorbed and re-emitted from atom to atom, moving in a random path. Amazingly, photons spend an average of 171,000 years traveling through the core and the radiative zone. Eventually, they enter the convective zone and spend about a month traveling there. During their long journey, photon energy is transformed from deadly gamma rays to ultraviolet, infrared, and visible sunlight radiation. This 171,000-year transformation makes life on Earth, as we know it, possible.
We know that fire results from the combustion of organic material and oxygen, but don't you still sometimes wonder what fire is? Why are gas flames blue and wood fire orange? And why do flames move in such a mesmerizing way? Chemistry may tell us the recipe for combustion, but the light show is all physics. When a flame burns cleanly, like a gas flame, blowtorch, or the base of a candle, the heat excites the molecules to release light, usually pale blue, from atomic transitions. That's quantum mechanics. Now, when the fuel isn't as pure and doesn't entirely burn, like wood fire, coal fire, or the top of a candle flame, there's still some blue light, but you don't see it because it's overpowered by light from all the particles of soot and smoke. They're glowing red hot. So why do hot objects glow? A process called black body radiation makes all objects glow with light of a color depending on their temperature. The reason that you don't see your friends glowing, though, is because we're too cool to glow with visible light. We glow in infrared. But lava, a hot piece of iron, or soot in a flame are all hot enough to glow with that familiar red-orange light.
Photosynthesis happens in leaf cells. They contain tiny organelles called chloroplast, which contains a green substance called chlorophyll. Chlorophyll molecules sit on the surface of the chloroplasts and capture light energy from the sun, which is fundamental for photosynthesis. Photosynthesis is a chemical reaction in which carbon dioxide and water are converted to glucose and oxygen by the energy provided from the light energy absorbed by chlorophyll. It is an endothermic reaction because it takes in energy from its surroundings. We show the light energy in brackets because whilst it is not a substance, it is an essential requirement for photosynthesis to happen. We could have written the equation like this instead. The equation is a very simple representation for a complex process, but is as much detail as we need to know at this stage.
Let's find out some more about the thing that brings the skies to us, the telescope. But before we can look into the different types, there are some basics we need to cover to understand why astronomers use telescopes and how they work. Different telescopes are necessary to see the universe in the different wavelengths of light. A telescope designed for visible light will be ineffective in the IR range, nor will it work if you're trying to use it to look for gamma rays. In this unit, we'll primarily focus on the telescopes that work in the visible range of light, which we call optical telescopes. But why do astronomers even use telescopes in the first place? What's the purpose? The sky is there, you just need to look. Well, there's so much more in the sky that the human eye physically cannot see, so the purpose of the telescope is to brighten and resolve what would have been otherwise invisible objects and magnify these. But what does it mean to brighten? When observing the night sky, objects that are extremely far may seem extremely dim. So telescopes can brighten this dim light by gathering so much more of it than our own eyes. In fact, the bigger the telescope, the more light is gathered. Think of the telescope as a photon bucket. Say, for example, you had 3 differently sized pails to collect rain. Which one would collect the most? The same concept applies to photon rain. Which of these photon buckets would collect the most photon rain? Clearly, the one with the larger opening has more volume to allow for it to collect more of the photons as they rain down onto it. So if the telescope can brighten dim light, what does it resolve? To resolve something in astronomy or photography lingo means to obtain the tiniest, minutest details of the objects that are being observed. And the resolution of a telescope is its ability to do just that. But remember, resolution does not mean focus. Our eyes cannot see past the visible range of light. So telescopes help expand our vision by seeing those wavelengths that we can't. Oh yes, and to magnify too.